In this video, we'll see what an instrumentation amplifier is and its use. In the video on bridge amplifier, we saw that while measuring physical quantities, we use transducers which change their resistance in response to change in the physical quantity. We used a bridge amplifier to convert this change in resistance into a proportionate electrical quantity. However, some sensors give a differential signal as the output so that we can eliminate the noise. We can write our differential signals as VCM plus VDM by 2, and VCM minus VDM by 2. VCM is called the common mode voltage and represents the noise in the signal. VDM represents the differential voltage and represents the actual information. We want to amplify this differential signal using a difference amplifier or subtractor, which gives a single-ended output. The output can be written as ACM VCM plus ADM VDM, where ACM is the common mode gain, and ADM is the differential mode gain. As we want to suppress noise and amplify the information, we want ADM to be much higher than ACM. Ideally, ACM should be 0. The merit of a differential amplifier can be determined by a factor called the common mode rejection ratio or CMRR. The CMRR is given by 20 log of ADM by ACM. Hence, CMRR should ideally be infinite. Consider the following difference amplifier. The value of the output is the following. Now suppose we choose R2 upon R1 equal to R4 upon R3. The output is given by R2 by R1 into V2 minus V1. Thus, for our subtractor we can write V1 as VCM plus VDM by 2, and V2 as VCM minus VDM by 2. Substituting these values of V1 and V2 in the formula of the difference amplifier, we get R2 by R1 into VDM. Thus, the differential mode gain is R2 by R1, and the common mode gain is 0. That means that the circuit rejects any common mode present in the input signals. In this case, the value of CMRR is infinity, which is what we want ideally. However, for this result, we have assumed R2 by R1 equal to R4 by R3. If there is any mismatch, then the common mode gain will be non-zero, and we will have a finite CMRR, which will lead to errors in the output. Hence, using the difference amplifier as it is, can be dangerous as we can get inaccurate measurements and amplified noise. Further, the impedances of the inverting and non-inverting inputs are relatively low and unequal, which will lead to different input currents when voltage is applied. This degrades the CMRR further. One way to improve the performance of this circuit is to add high input impedance buffer amplifiers ahead of the simple subtractor circuit. This configuration is called the 3-op amp instrumentation amplifier. This circuit now provides matched, high impedance inputs so that the impedances of the input source will have minimal effect on the circuit's common mode rejection. The 2 op amps on the left now handle the driving of current through the resistors instead of letting the input voltage sources do it. The increased complexity of the circuit is minimal, but the benefits are huge. We can further improve this circuit by enabling variable gain. This can be done by adding appropriate resistors in the feedback path. This circuit is called a 3-op amp variable gain instrumentation amplifier. Due to the virtual ground condition, the voltages at the two ends of R1 will be V1 and V2. Hence, the voltage drop across R1 is V1 minus V2, which is the full differential input. Another advantage of this circuit is that once the subtractor circuit has been set up with its ratio-matched resistors, there is no need to change these resistors. The gain can be changed by simply varying the resistor R1. Using superposition for the second stage, the output Vout is given by Rf by Ri into V2- minus V1-. Similarly for the first stage, R1 upon R1 plus 2R2 into V2- minus V1- is equal to V2 minus V1. Hence, Vout is equal to 1 plus 2R2 upon R1 into Rf by Ri into V2 minus V1. If a common mode voltage is applied to the amplifier inputs, the voltage at both ends of R1 will be the same and no current will flow through this resistor. Since no current flows through R1 and hence, through both R2s as well, these op amps act as unity gain followers. Therefore, the common mode signals are passed through the input buffers at unity gain, but differential voltages will be amplified by the factor 1 plus 2R2 by R1. This means that by varying R1, we can increase the differential gain of the circuit as we want, but the common mode gain will not increase. Thus, we can increase our CMRR as much as we want in theory. Further, because of the symmetry, common mode errors in the input amplifier tend to be cancelled out by the output stage subtractor. The instrumentation amplifier is usually available as an IC, and we represent it as the following. Here, R1 is chosen as AR while all other resistors are chosen as R. The output is 1 plus 2 by A into V1 minus V2. That's all for the instrumentation amplifier. If you have any doubts, please ask in the comments section below. Don't forget to like, share and subscribe.